Yeah.
All right, there we go. We got the recorder up and running, and I think it's time to get started. So I'm going to, right after this class, I'm going to the Liberal Arts Replacement Building Project Design Committee meeting. Okay. So basically, they're going to take input from faculty and administrators about, how, what ideas they want to incorporate and what criteria they want to incorporate into the building that is going to replace all of these liberal arts buildings. But interestingly, there's no student representation.
Because we'll all be gone before it's here.
Well, yes, but there will be new students, right? So the idea is, I don't know what kind of criteria they will specify, and from whose perspective they will be specifying those criteria. Okay, because I only see things from my perspective, which is on this side of the classroom. So if I were to walk over here, this is a new perspective for me. Okay, I never really see myself. I can kind of see a virtual tech walking along there and talking, and pointing out things. But this is not my usual perspective. I'm standing right now. If I were to sit down, okay, and I'm kind of short, I can see how the top 2/3 of the screen is really visible to me, but the bottom 1/3 is kind of difficult for me to see. So that's why in these kind of meetings, I think it will be helpful to have some kind of a student representation. I talked about this with my previous class already, and I'm not going to do the whole presentation in this class because we're kind of running out of time for this class. We need the time for class material. But let me just ask you this, okay? If I have a tablet, okay, and the tablet is connected to a, some kind of a screencast engine, so that you have your own laptop computer or your own tablet or some kind of mobile device where you can see what I'm doing on my tablet, including the screen itself, and if I need to, I can freehand draw stuff on it like a whiteboard. Can that take the place of a projection screen? That's the question. You think so?
Depends on the size. Depends on the size and
the size of what?
The screen.
Of your own screen. Okay. So what kind of devices do you see yourself taking to a university? Because in 2019, I think some of you will be in a 4-year university. So what kind of device do you see yourself bringing to school as a tool for learning?
VR.
15-inch monitor, 16, or just a tablet with a 10-inch, screen. I mean,
they have glasses that project 27 inches. You can see.
Yeah, ocular projection. Okay,
Yeah.
so that's a possibility, but in 2 years, I don't think those devices will become, too popular.
Yeah.
Yep.
I feel like in 5 years, you won't even have to go to school necessarily physically to get the degrees. I mean, a lot of the Ivy League schools are already putting most of their curriculum online, with video and audio courses and stuff like that. So, and those are accredited courses.
So don't make a new building.
I mean, not necessarily. You may not necessarily need to bring anything. The classroom might come to you.
Okay.
And that whole online creative space sharing, like you're talking about, is the technology's been there to do that for a long time.
Yeah.
It's just the implementation on a bigger scale hasn't been done, in our case at least.
So with a class like this, okay, would you take it online? Would you prefer to take it online, or would you prefer to take it in person?
In person.
Most people say in person, okay.
But the materials is what I'm saying, is everything, like how you record your class. You know what I mean? So you don't necessarily need to bring anything because all the resources are available to you online.
Right, but when you're in class, you still need to see what I'm talking about, right? Because I would look at this, I would say, okay, let's take a look at this algorithm that initializes an array. Okay, so in a classroom like a conventional classroom like this one, I will put it onto the projection screen so that you guys can all see what I'm talking about. Okay, so the question is, if I do not have a projection screen anymore, and instead the only way for me to distribute what I'm looking at or what I want you to be looking at is a digital thing where it will display on your own screen, or if you choose to subscribe to that screencast, would that suffice? Would that replace the actual projector screen?
Are these devices being provided to us, or we have to buy them to bring them to us?
I think in 2019, which is the completion date of the project, it will be so inexpensive to have your own tablet that if the tablet can replace textbooks, I would say everybody is going to have a tablet. Okay. So but the question is cost not taken into consideration. Is the screen size sufficient? Right in front of you with I think this is about a 14. Would that be sufficient? I think for people in the back over there, your own device is going to have a bigger screen. In terms of view angle, it's going to be better than looking at the projected screen image over here. Is that making any sense? So would that be sufficient to replace all of that stuff? Because if that is sufficient to replace this, then classrooms don't need to arrange like this anymore. You don't all have to face in one direction. We can have tables where you guys can face each other, and I can just be walking around the classroom when I lecture because I'll be holding my own tablet and drawing stuff and typing on it. Yep.
Battery life. There's a consideration. Battery life.
You can charge your device while you're
Are
in
there going to
class.
be chargers at the desk?
Yes,
Okay.
that is part of what I want to specify already.
I was gonna
Okay,
say.
that is going to be a requirement that I want in every single classroom is BYOD charging stations. Okay, if you want to bring your hair dryer, that's a whole different story. That would just cause a building blackout.
But it's my industrial strength hair dryer, and I can't live without it.
Then you will have to bring your own diesel generator. Park it outside. All right. So I'll bring those ideas forward today, because that opens up a lot of possibilities. Because classrooms do not they don't have the structure like a regular classroom anymore. Because using that type of technology, see it's turning red already, which means the battery is running out, and I don't see the replacement battery anywhere over here. Okay, I got 2 more. So when it runs out, I can change the battery. All right, so we'll continue the discussion of arrays, and what we'll do today is we'll focus on the homework assignment, because I know you guys have nothing to do next week. But spring break, right? I mean, why would we take a break in the middle of a semester?
Why would we start the second 8-week classes on Wednesday before spring break?
Yes, there's that. Okay, so here's your new homework assignment. It's called binary search. Okay, it's a trace type of homework assignment, just like your usual trace homework assignment. There's a starting point file. Okay, let me just download that file and I'll show you what it looks like. Okay, there we go. Open this. See, right now you guys are all looking at the screen, but sometimes when I walk around, you would turn your attention back to me and look at me. This is one of the worst arrangement where the screen is on one side of the classroom and I'm on the other side because this is where the keyboard is. Okay, so this is the algorithm itself. Okay, we should, other than only one of the things, we should understand everything about this algorithm. The only one thing that we don't necessarily understand at this point is what is floor. Okay, the floor function in mathematics. So that's an easy one to define. I can tell you exactly what it is. But other than that, we don't have anything new. Okay, bar A bar, we talked about that already. It's the number of elements in an array. The square bracket thing, that allows you to specify a particular item in an array. We have a repeat until. This is one of the rare cases where we have a post checking loop instead of a pre-checking loop. Because we cannot, this type of algorithm does not lend itself to pre-checking, so this is one of the very few cases where post-checking makes a lot more sense than pre-checking. Okay, so let's talk about the floor function, because it only takes a little bit of discussion. It is in my notes already, so if you have been reading my notes, that's already done. Okay, the floor function is also known as this symbol in mathematics. Okay, but in When I type, I don't have the option to specify the floor symbol in mathematics. This is basically the largest integer. Okay, I take it back, the smallest integer. So erase, where's the eraser? Okay, so in here. Okay, it's the smallest, or the least. The least integer that is greater than or equal to x. Oof. Okay, here we go. So let me see if you understand this concept. What is this? What is the least integer that is the least integer that is greater than, I think I got it backwards.
3.
Okay, I got it right, I got it flipped, sorry. My bad.
Less than.
This is the largest, and then the other side is less than or equal to. Okay, there we go. That makes more sense.
Okay, now it's 2.
Okay, so with this redefinition, what is it? This is going to be 2. Okay, very good. What is the floor of 2.7? 2. What is the floor of 2? 2. What is the floor of 2.1? No.
1.
No.
Oh, negative 2.1. Sorry.
No.
It would be
0.
No.
negative 0.
The floor of negative 2.1 is the largest integer that is less than or equal to negative 2.1.
Negative 3.
Negative 3 is the correct answer. Very good. Okay, there we go.
Okay.
But since indexes cannot go negative, we don't have to worry about the negative side. We only have to deal with the non-negative floors. Okay? So that's what the floor function does. Okay? All it does is to turn something that is not an integer into an integer. Okay? In the algorithm of binary search, I could have used ceiling, which is the other way. You know, the way I defined it earlier is the ceiling function. Okay? Because it's the smallest integer that is greater than or equal to the number. This is called the floor function. You could use the ceiling function too. That will work just as well in binary search. We just need a way to convert a convert 2.5 to either 2 or 3. That's all we need. All right. So the only mystery part is now done. This is the binary search algorithm. And in your homework, what you need to do is to trace it. There's 1, 2, 3, 4 sheets that you have to go through to trace it. Okay? So you just have to go through the algorithm. Okay? It's for the most part already formatted. All you have to do is just to fill it in, trace it, save the file, turn it in, okay? And you have until the Wednesday after spring break to turn it in. In other words, if you say, but I want my spring break to be my spring break, I don't want to work on anything during spring break, fine, you still have 1 week to do it. Knowing most people, you need another week to recover from your spring break. But I cannot accommodate that. All right, so this is your homework assignment. So what we'll do today is to go back to binary search, okay? And just for the moment, unless you have a photographic memory or you already know the binary search algorithm, most people would not remember anything about the binary search algorithm, except that it involves the floor function and a post-checking loop, okay? Which is great, because I want to help you develop the algorithm today after I describe how it works. Yes?
Doesn't division already truncate, so wouldn't that work like a floor function?
Correct. In C and C++, division is already an integer division, which means you do not need a floor function. But in many other settings, the division is not always giving you an integer, so a floor function is needed. But in C and C++, the floor is automatically applied. Correct. That's a good point. Okay, so let's start from scratch. Okay. So what I want to do is to give you an idea of what is binary search. Binary search is a really cool search feature because, well, let's see. Maybe I should kind of bring that up or not. There's several things that I want to bring up. One thing that I want to bring up is when you're searching in a sorted type of list, okay, you can do it a lot faster compared to a non-sorted list. I'll give you one example, phone book, okay? In a regular phone book, which is sorted by last name of people, the white pages, if I tell you the name, the last name of the person that I'm looking for, it won't take you a whole lot of time to either find that person in the phone book or confirm that person is not on the phone in the phone book, right? Because it's pretty easy to search. On the other hand, if I tell you, okay, I want to find out who owns this particular phone number, and the phone book is not sorted by phone number, then it will take you a long time to come back with an answer. Because if the phone book is not sorted, you have no choice but to go through the phone book entries one by one until you either find the number or you run out of pages, okay? Then you can conclude and say, oh no, that person or that phone number does not exist in this phone book. Is that making any sense? Okay. So what I want to talk about today is called binary search. Now binary search is really, really interesting because it's very, very efficient. Okay, last time I think I talked about this already. With a world population of 7 billion, and assuming that each person has an entry in a particular array, to find out whether a person is even there or not, using binary search, I only need 33 comparisons. Now how does that work? Okay, so let's take a look at this example. This is one of those cases where a simple example is not going to illustrate the effectiveness of binary search, so I'm going to use a long list to illustrate the point of binary search. So I'm going to start with a random number, and I cannot remember how to use random number here, so I'm going to cheat a little bit and say insert function, and we'll look for, I think that falls into math, and we look under random. Okay, so random number between is probably what I want, okay? So I'm going to use random number between, the first number is not that important, so between 1 and 10 is fine, okay? So this time it gives you a number of 2. The next number is going to be the previous number plus a random number between, well, I can just use, between 3 and 20 for each number. And now I can use this feature of the spreadsheet to keep going and going and going until I have 511 entries. Which is a lot, okay? So 511, which is right here. Stop. Okay, so now I have a lot of numbers, okay? And I have no idea what those numbers really are because they're all kind of random, okay? Or I should say the gap between these numbers is randomized, okay? All right, so I want to look for, so we can kind of tell the range is going from 2 to 5,700 or so, 58, okay? So let's pick a number. I'll let you guys pick a number.
72.
Okay, let's pick 72 and then we'll do with the other number next, okay? 72, so the question is 72 a part of this list, okay? What are you going to do this? Well, instead of going from the beginning and look for the number 72 in a linear way, I'm not going to do that. I will go straight to the middle. So when you look at 511, which entry is smack in the middle of these 511 items? The entry on row 256. 256, okay, because I chose a odd number for a reason, okay? So 256 is the one smack in the middle. So I scroll to 256. Now remember, when you're doing array indexing, there's no scrolling, okay? You go straight to that row. 256 is this number, okay? Does that look like 72 to you? No, it doesn't look like 72 to me. But is this number greater than or less than 72? It's greater than 72, which means 72 cannot be below this point. because every number below this point is greater than this number already. This array is sorted. So I know 72 has got to be in the first half. Okay? Oh, did I just use the word half? Yes, I did. Which means every time you compare, you can throw away 1/2 of the remaining choices, which is great, because after one compare, I can say, oh, the other 255 elements cannot be the number that I'm searching for. That's only after one single compare. So after this, where do I go? I just confirmed that entry 256 or row 256 is not the number that I'm looking for, but it is greater than the number that I'm looking for. Where should I go next? 128, very good, because you chop it in half, okay? So you look for the midpoint every single time. So I go to 128, okay? Now once again, remember when you're doing indexing, there's no need to scroll. We're doing scrolling only because of the limited user interface. This is row 128. The number is 1430. That doesn't look like 72 to me. So what I do is I throw away the second half again, okay? Because I know the number has got to be from entry 1 to entry 127. Where do I go next? What is the midpoint between 1 and 127? 64, very good. So we go to entry 64. Pretty sure there's a quick way to get to cell 60 or row 64 with just a few keystrokes. I'm just not familiar enough. Well, that looks like 72, but it's not. Okay, it's 10 times 72. But it's also too big, so the next number is going to be 32. Still too big, 16. Still too big, and 8. Still too big. And then we go to 4. Too small. Now this is where we go back again to 6. And then we go to 7. And now we conclude the number is not there. Okay? So this is binary search. Every time you compare, you eliminate 1/2 of what is remaining. Until you have one choice left, then the only answer is yes, this is the number that I'm looking for, or no, the number is not in the array. Is that making any sense? So when you look at the number of entries we can handle per comparison, let's take a look at the separate spreadsheet. Okay. So here's the separate spreadsheet here. Yep, go ahead.
So does this only work when it's
Sorted.
Sorted,
Yep.
integer numerically? Okay.
Yep. You can well anything that is totally
Not when
ordered,
it's sorted.
that's completely ordered and sorted, we can deal with that. So it can be names, can be zip code, can be social security, stuff like that. So anything that can be sorted, we can use this search method.
I mean, with names and stuff, is the sorting arbitrary or is it alphabetically?
If it's name, it is sorted alphabetically. You can either only use last name, or you can have a combination of last name and then first name. So we want to look at the number of comparison as opposed to the size of the array. Okay, like how many comparisons do I need if I have an array of this size to confirm whether a particular value is in the array or not. Okay, so let's take a look at an array of only one element. And people would say, but why would you have an array of only one element? Because just for discussion purposes. Okay, so if you have an array that only has one single element, how many comparisons do you need to confirm whether that one single element is what you're looking for or not?
One.
Only one, okay, very good. So you put a 1 here. What if it has 3 elements? Well, I skipped 2, okay, for a good reason, but let's say it's 3, okay? So with 3 elements, how many comparisons do we need to confirm whether a particular value is in the array or not? The first comparison is going to be right in the middle, and we'll just chop it into 2 halves, and then the second comparison only has 1 entry to deal with. So we need 2 comparisons. Does everybody see how 2 will do it? Because when you have an array of 3 elements, which is like this, we always look in the middle first. So let's say we're not lucky, this number is not what we're looking for. But that means we only either have one element left as the last one, or the other element left, which is at the beginning, to compare to. But when it's down to only one single element, we have the same situation as the previous row, where there's only one element left, and you only need one comparison to confirm whether that is what you're looking for or not. Is that okay? Okay. So the next one up, the next size up is 3 times 2 plus 1, which is 7. So with 7, we only need 3 comparisons. Because with 7 elements, after one comparison, we have 2 chunks left, okay? But only one chunk is possible. But that chunk only has 3 elements. But we already know that with 3 elements, you only need 2 comparisons to come to a conclusion. Is that working out okay? So if I work this out, the next one is going to be, what is the number of elements in the array for the next case? Twice the previous row plus 1. 15, okay? So 15, I need 4. The next one up is going to be 31, I need 5. So there's a general equation to do this. This cell is this number, the one from the previous row, times 2 plus 1. This one here is just the previous row plus 1, like that. So I can now use this general equation and work out the numbers a lot faster, because now I'm using the computer to do the calculation. It's basically exponential, okay? It's basically exponential, which means the number of comparison is the log of the number of elements in the array. Now this is a very powerful feature, because when world population becomes 16 billion, okay, I only need 34 comparisons instead of 33. Because every time you double the size of the array, you add 1 comparison. And it's a very powerful technique. Are there any questions about how binary search works? No questions? This is all good? Okay. But why do we need to understand stuff like that? Okay, because linear search is cool. Okay, it's very simple to code, and it's just easy to understand. So with linear search already being able to get a job done, why do I need to know about binary search? It gets the job done quicker, but what does that translate to you as your bottom line? What are you going to do after you take all the classes here, after you complete your bachelor's degree or master's degree? Eventually you have to get out of school. Okay? So what do you do when you get out of school? I move back to with my parents.
Continue minority operation.
No, we don't do that. Instead, what do? We want to get our own jobs, right? And many of you, even if you are not going to be a professional developer or programmer or software engineer, you will still be writing some code, because otherwise you wouldn't be here to take this class, okay? So if you're going to write code, okay, maybe not professionally or for a living, why would this stuff matter to you?
Because you can apply it to just about anything.
You can apply it to just about anything, but the bottom line is it helps you keep your job, not getting fired. I would say that's a kind of important aspect of getting income and stuff like that, right? Okay. So what I want to do now is to take a look at another algorithm. Okay, so we'll go ahead and do something like this. I'll insert a column to the left-hand side and insert a row on the top here. Okay. So column B is really just talking about, in binary search, how many comparisons do we need to come to that conclusion that a particular value is or is not in an array. Okay, so that's what this column is. And then on this column, I'm going to look for linear search. Okay, linear search, which is just looking through the entire array one by one until you find it, or until you run out of entries in the array. Okay, so we want to take a look at the comparisons here as well. So with an array of 1, yeah, they're both 1. When the array has 3 items, guess what? With linear search, you need 3 comparisons. the worst case is you need 3 comparisons. And it's only the worst case that we worry about, because the best case is the first thing you look at is the one that you need, so it's not really that useful. So now you can start to see the differences between the 2 algorithms, 2 approaches to get the same thing done. They're both correct, they can still get the job done. But one will require 16,383 comparisons in the worst case. The other one only need 14, worst case. Okay? It matters because it means one algorithm scales a lot better than the other one when the size of the problem increases. Is that making any sense? Okay? And it matters because if you choose one algorithm that is not efficient, and somebody else, a competitor company, choose an algorithm that is efficient, then your product is going to lose out, because people will look at the speed differences between the applications and go like, hey, this program is going a lot slower to get the same thing done. Why is it going a lot slower? Right? And if you are the one put in the slow code instead of the more efficient code, then your boss will be on top of you asking, why did you choose this code instead of the other code? And this is costing our product to lose market share. And if the economy is not doing well, whoever put in the inefficient code is going to get fired. Okay? That's the bottom line. And I think that is important to you because you don't want to lose your job because you chose the wrong algorithm. Is that okay? Now, is this really that important? That's the second question. Okay? To illustrate how important this is, I'm going to have a little scenario here. Okay, so this is Tag's computer. And the next column is going to be Pat's computer. Okay, again, Tag's computer. And this time we are actually trying to see how much real time it takes to complete the algorithm. And this is Pat's computer. So this is the scenario, this is the situation. The company is downsizing. It's down to me and Pat. One of us has to go. Okay, the question is, well, who is going to get fired? Who's going to be let go because the company has to downsize?
Both of you.
Sorry?
Both of you. It'll be outsourced.
It'll be outsourced, very good. But if it's just one of us, okay, if it's just one of us, the boss says, okay, let's have a programming contest, okay? Let the most skilled programmer or the most efficient computer, in this case, win. Okay, so the boss doesn't understand anything about what we call time complexity with algorithms. The boss just says, hey, if it takes your computer 5 seconds to get the same thing done, and it only takes the other computer 2 seconds to get the same thing done, the computer that takes 5 seconds is going to lose out, and whoever uses that computer is the one getting fired. Okay? So that's the boss's understanding of algorithms, time, and stuff like that. Okay? Okay, so this is a multiplier, okay? Now, because I joined the company really early on and I never asked for an upgrade of my computer, I'm still running a 386 computer. Okay? So how long ago, what is the age of a 386 processor? Right?
90.
It's about 92, okay? So let's figure out what is the speed of a 386 computer processor compared to a current generation i7 processor. Okay, so we'll take a quick guesstimate here.
First, there's only one.
Okay, the 386 processor came out in, let's say, 1992, right? That's not that long ago. Okay, so we have an i7, the latest generation of i7, because i7 spans across multiple years. So we are talking about a new, brand spanking new i7 processor, 6-core, hexa-core, and all that stuff. And the time is 2016, okay? Okay, so there are how many years in between? 24 years, okay, that's not a whole lot. Just enough for someone to get through college and graduate and get a bachelor's degree, okay? Which is not really that long, just one generation. Okay, 24 years. So in 24 years, what is going to be the speed difference between these two chips? Okay. What do we use to guesstimate that? We use Moore's law. Okay, Moore's law says the speed of processor. Well, it doesn't quite say the speed, but it says the density, which translates to speed. Okay, so it says the speed of computers chips will double every 18 months. Okay, that means 18 months is important. We want to figure out how many 18 months do we have in 24 years. Okay, that's a pretty easy number, 16, right? But so does that mean that the i7 processor is only 16 times the speed of the 386? No, because every 2 years it doubles. Every every period, okay, every 1.5 years it doubles. Every 3 years it quadruples. Every 4.5 years it eightfold, okay? Every 6 years it is 16-fold, and so on, okay? So we are talking about not 16 here, because there's 16 1.5 years between in 24 years. We're talking about 2 to the power of 16, which is 36, sorry. Okay, that's the estimate of the speed difference between a 386 in 1992 and the i7 processor that came out this year. Okay, whether this number is actual or not, I don't know, but I think the order of magnitude is probably about right. Okay, so here's the competition. So the multiplier in actual time is everything that I do is going to be a lot slower because the computer is slower. So when I use my Smarty Pant binary search algorithm, I have to remember to multiply the time penalty, which is 2 to the power of 16. So in terms of unit of time, where Pat's computer only will take 1 unit of time, mine will take 65,536 units of time. I don't care what unit you use to measure, okay? It can be nanoseconds, can be milliseconds, I don't care, because I'm only interested in the factor of difference, okay? But Pat is choosing the easy algorithm. The first one that he or she can find on the internet for searching is linear search, okay? So the boss look at this number, look at these two numbers and say, Tech, I'm sorry, but you are going to be the one that has to go because your computer is so slow. Okay, your implementation is so slow. There's no doubt in my mind. So I tell my boss and go like, well, let's make the problem bigger. Okay, let's make the problem bigger. My boss look at it and go like, Tech, I can see the difference increasing between how much time your computer takes to solve the problem as opposed to Pat's computer. Okay, and Pat says, yeah, I'm going to take your Windows seat. Okay, and I go, well, let's make the problem even bigger. The boss says it's not helping. Okay, and I keep insisting, let's make it even bigger. And Pat agrees because Pat thinks this is entertaining. Okay, so let's go. So we'll do a little fast forward here. Okay, and guess what? At this point, Pat is starting to feel a little pressure because Pat is realizing that the increase of time of his or her own computer is faster than the increase on my computer. Because my computer is just increasing but very steadily, okay? But the amount of time on his or her computer is increasing, well, kind of quickly. Okay, so
I've already gone through 16,000. Your boss is like, well,
yeah. So we keep going. It won't take long. Trust me. It is not going to take long. All right. Where's the crossover? The crossover is 131,071 problem. That's when my algorithm my computer ended up taking less time than Pat's computer. Even though I'm using a 386 circa 1992, and Pat is using a brand spanking new i7 processor.
you have 2 million numbers to be able to overtake it.
Yeah, but 2 million is nothing. Okay, what is the population in Sacramento area? So million is nothing. I mean, these days, that's not a huge number. Yep.
I just had a question. What if you had an i7 as well in this?
That's the time.
Then I would have smoked, Pat from the get-go. That would not make it very entertaining. This is a lot more entertaining, just to see Pat's hope getting up. Oh, wait. Oh, that dramatic effect, is not going to be there if I started off with an i7 to begin with.
You didn't get the window seat.
Then you're 3 comparisons and your boss like, yeah.
Well, Pat is going to get a door seat because not a window seat. Yeah, his or her office is going to be somewhere else.
You get a window seat.
But the problem with this thing is the shape of the curves are different. Okay, it has to do with the shape of the curve and not so much the multiplier to the curve itself. So when you plot these numbers out, this axis is indicating the number of elements in the array, and this axis is measuring the time it takes. Linear search, as the name implies, is linear, which means the time it takes to complete the algorithm is proportional to the size of the problem. Binary search is a log n type of issue, where the curve is a log. In other words, if my computer is even slower than that, it will just take the problem size to be bigger to beat the other computer. It's eventual, it is inevitable. Okay? And this is a big deal. It's a big deal because if you choose the wrong algorithm, then your implementation is going to get slower and slower as the size of the problem gets bigger and bigger. So choosing the right algorithm is important. How many of you are going on to a computer science program or planning to go on to computer science? Okay, there are a few. Okay, so those of you who are moving on to computer science, there will be a class called algorithm analysis, or the analysis of algorithms, where they will prove to you that there exist no search algorithms faster than binary search. This is as fast as you can get. Okay? Yep.
Could you somehow combine those two algorithms?
Combine those two?
Like you would combine a function for that first section where the linear is faster?
There might be some algorithms falling in between these two, but I really don't think that those are popular because these two are the most common search algorithms. Okay? Yep.
Well, couldn't you create like a complex algorithm that uses the linear formula until you get to a certain number based on the processing power? Obviously, how you add the proportion and then switches over to the log method. I think that's what.
But the log method always wins.
Right, but
There's
with
no
a bigger sampling size, so it would be more efficient to use the other method on a smaller sampling size.
But it's not.
Be able to alternate.
But linear search is never more efficient.
The only reason it was more efficient is because he had the time delay from the 1992 processor.
Yes, that's the only factor.
That was
Yep.
the only reason.
Yep, it's never any less efficient. It's just that my boss did not understand the whole concept of complexity or the curve of the time versus problem size. So I just have to keep pushing it until the problem size shows that my algorithm would take less time. Okay, is that okay? Yep, go ahead.
Okay, so on that graph, shouldn't that curve be lower than the line?
Say again?
Based on what you said, shouldn't that curve be lower than the line?
Well, this is my computer because my computer is so slow to begin with. So initially it's losing, but over time, it will beat the other algorithm. But because of the shape of the curve, it really is just a matter of time. Even if I use a computer even older, okay, it will just take a larger problem size for my computer to start to go faster than Pat's computer.
If your Commodore 64 and told you that.
And that's just going to bump the problem size up by another 4, 6, 8 fold, and it will happen eventually. Okay. Any questions about this part? Now, the flip side of this type of discussion is really, really important as well. In other words, there are problems where they're so tough, there are no efficient algorithms to solve those problems. They're called intractable problems, which means they are solvable, but the solution is going to be time consuming. There exist no efficient algorithms to solve those problems. I'll give you an example. The most famous of these algorithms is called the traveling salesman problem, okay? Which is like this, okay? So think about pizza delivery, okay? So you have, this is the pizza shop, okay, pizza. Okay, so the pizza shop is kind of right in the middle of the 4 delivery points. So we have point A, B, C, and D. So the question now is, how should I plan my delivery route so that I can get back to the pizza place as quickly as possible for the next delivery run? That's the question. Okay, this one is not tough because you can actually quite easily look through all the possibilities. How many possibilities are we talking about? How many ways do we have to go through all these routes? Okay. Out of the 4 destinations, how many choices do you have as the first destination of this route? 4. Okay, so you have 4 choices for the first one. But once you get to that one destination, how many choices do you have left as your second destination? 3, 2, and then once you have all 3 nailed down, the last one, you don't have a choice because that's the only one left. So that means you have 24 possible ways to arrange the destination points A, B, C, D. With a computer, it's not difficult to have, you can even use the Google Maps API and actually program, write a script to go through all 24 possible routes and find out which one is the quickest. And just say, okay, this is the quickest one, and your truck is going to take that route to be the most efficient one. Does that make any sense? Okay, so let's just say that you have that algorithm written, your pizza house or your pizza place, the boss is really happy about it because it's saving gas, it's saving time, it's saving money for the pizza shop. Okay, so you're the star employee of the month.
As long as it updates via track.
Sorry?
As long as it updates for track.
Yes, well, but Google Maps automatically take that into consideration. So this is perfect. And this applies even more in San Francisco, because in San Francisco, a lot of streets are one way, okay? So, how you traverse the ordering of the ABCD points, makes a big deal, okay? Traversing it in the opposite way can easily take twice as long in San Francisco, okay? So your boss is really happy. So one day, your boss summons you to his or her office and say, you know what, I'm gonna fire you. What? I was the star employee from the previous month, why are you upset with me? Your program doesn't work. See, this is what I really don't like about people complaining when they're not specific about what is wrong with it. Your program doesn't work. What do you mean by my program doesn't work? I've been doing this route planning for the entire month, and every single day, we are saving money, saving gas already. Yeah, but you know what? My buddy said, that your program doesn't work. Which buddy of yours? You know that guy who owns UPS, who operates, UPS in San Francisco? He said this program doesn't work. We go like, well, the algorithm is supposed to work regardless. And then I asked, how is it not working? Your program just hangs up. It doesn't come back with any results. We're like, that's kind of curious. How many drop points do we have on the truck, UPS truck as a route? Okay, how many points does it have to visit in each day? Well, it's not a pizza delivery truck, right? It is a UPS truck. So what do you think is a reasonable number of stops on a UPS truck per day?
300.
Probably in the order of 100. Okay, I would guess it is about 100. Okay, so you say, okay, 4 stops versus 100 stops, 25 times. Okay, if it only takes 2 seconds to get this done, okay, this should be completed in a minute at the most. Okay, so if the program doesn't come back with a result, it's broken. Tag, it is broken. Boss Boss, it is not broken. This is a tough problem to solve. Why is it a tough problem to solve? We can do with 4, so this is only 100, it's only 25 times more. How can that be a big problem? Boss, you're not understanding this. The time it takes to solve this problem is not proportional to the number of stops. It is proportional to the factorial of the number of stops. Boss says, oh, exclamation point. So are you being smart with me now, using an exclamation point and trying to make a point here? No. This is factorial. Factorial means 4 times 3 times 2 times 1 for 4 factorial, and for 100 factorial, it means 100 times 99 times 98, blah, 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 all the way down to 1. The boss has absolutely no idea about the actual value of this product. You go like, yeah, big deal, how is that any different than, just 25 times this number? Boss, how about this? We use a spreadsheet to find out what the value is for 100 factorial, as opposed to this number, which we already know is 24. So I went back to my trusty spreadsheet and asked the spreadsheet, tell me what is the factorial of 100. And it gave me a number. Boss, look at this number and go like, so it is 9 plus 157. It's what? It's 160 something, okay? Versus 24, okay? What is the big deal? I don't understand this. Boss, this is scientific notation. This is 9.333 times 10 to the power of 157. I still don't get it. Okay, boss, this is what is happening. This number is 9.333 times 1, and I spent 2 minutes to write down all the zeros. 157 zeros, all the way up to here. Oh, now I'm starting to get it. But I'm still going to fire you for using such a stupid algorithm. Boss, there's no smart and quick algorithm to solve this problem. Really? Are you saying that you're the smartest person on the planet? No. But throughout the history of computer science, since the 50s, okay, nobody has found a faster way to solve this problem. This is called an intractable problem. Yep.
Is this something that quantum computing addresses, one of these kind of problems? Or
That's a good question. We'll probably get to that point. So just kind of keep that thought in your mind. Okay. So my boss go like, oh, okay. So I guess it really is a difficult problem to solve. Okay. So as it turns out, this is a problem called NP complete. Okay. So we'll talk. I'll just give you an exposure of what is NP complete. NP complete refers to an entire classification of problems that cannot be solved efficiently. And so people ask, but what is NP? NP stands for non-deterministic. Deterministic. Okay? And P is polynomial. Okay. Which basically means if you have a magical processor that has an infinite number of cores, whenever you need to start a new thread, hey, magically a new core just starts to exist. And there's an infinite bandwidth to memory, so they can all share memory with no cost whatsoever, with an infinite amount of cache. Okay, so it's a magical processor. Even with a processor like that, it will take polynomial time. Polynomial means the time that it takes to solve the problem is proportional to a polynomial of the size of the problem. Can be linear, can be squared, can be cubed, and so on and so forth. Okay? And the traveling salesman problem is one of these problems. Okay, it's called NP complete. So getting back to your point of quantum computing and stuff like that, if a quantum computer can spin off as many threads of execution as I need, then it will become a polynomial time algorithm. But even with that, it is still a polynomial time algorithm. Okay, so do we have any questions about all of this stuff here? And why, yeah, go ahead.
So what you're saying is the ridiculous numbers still the same, but quantum computing would be able to tackle it in a
Because you
realistic
can,
time?
exactly, because with a quantum or a computer that can go in parallel, you can basically explore one of these paths. Each processor
All
can
at the
handle
same
one
time.
alternative all at the same time. So the amount of time it takes is polynomial to the number of stops, because you still have to add. That adding part is linear. Is that making any sense? But that's the kind of problem that we're dealing with when we have the traveling salesman problem. And the understanding of algorithms and intrinsically how much time it takes to solve the problem is important. Because if you know this ahead of time, then you might have told your boss and say, this is only practical for up to 6, 8 stops, okay? But don't try to apply to any more than 10, because it's going to be inefficient after a certain number. You can give your boss an estimate, okay? If it takes 2 seconds for this kind of problem size, it's going to take an hour for this problem size and go no further, because the next one up is going to be a day or 2, right? But knowing this, you have just armed yourself with the ability to keep your job, because now you can argue with your boss. Do you guys kind of see the value of this type of analysis? I'm not going to tell you, how to derive the equations, how to come up with the math, because that's all on Wikipedia already. Okay, but how you make use of this kind of concept is called time complexity, is very important. And just personally, I suspect with certain big software publishers, they choose algorithms not so wisely, and that's why sometimes certain programs run so slowly when it doesn't need to be run so slow. Is that making any sense? Okay. All right. So are we good with this stuff here? Kind of. Okay. All right. So now that we know binary search is good because it is good for retaining your job and all kinds of stuff like that, let's figure out the algorithm to do this. Okay. So this time we'll go pick a number that is not right, sticking to the one part of the array. We know the numbers go to what, 5,800 or so. So we'll pick a number that is kind of maybe two-thirds through the whole thing. So that would be about 3,000-ish. Okay, so let's pick 3001. Okay. All right, so we'll go ahead, and what I'm doing right now is I am emulating the process of doing this manually. Because until I can do it manually and figure out what is the repetitive part, what is the logic of it, I cannot write the code to do it. Okay. So I'm going to say, let's go ahead and look for, so the value of the key, okay, the K is 3001. Okay, this is the value that I want to search for in this entire array. Okay, I'm hoping it's not there because otherwise it doesn't help to illustrate the concept. Okay, so the first time I run this algorithm, what is the range of the entire array that I have to look to see if 3001 is there or not? Pretty much the entire array, right? Because before the first comparison, I have no idea, where 3001 might be in the entire array. So I need to first, say, okay, with the first iteration, we have to search from item 1 all the way up to the last item. Okay. Now using the indexing of what we talked about, it's going to be index 0 to index 510 because we have 511 elements in the array. So this is the range of the index. Okay, out of this range of the index, I'm going to insert one more row here. Which one is in the middle? Divided by 2, right? Okay, so 0 plus 510 divided by 2 is 255. Is in the middle. So we go straight to item 255, And I need one more column to do the indexing because I cannot do the math quickly enough. So we'll just do some indexing here. This is 0, and we just extend the whole thing down to the last item, which is here. Okay, so now that we have the indexes, we go to 255. Okay. And 255 is right here. Okay, so we look at the number at index 255. The value of that element is 2891. Is that greater than or less than the number that I'm searching for? It's less than the number that I'm searching for, which means can I toss away the top half of the array or the bottom half of the array? The top half. Okay, so I have to keep the bottom half, which means from index 256 to the end, I have to keep. Okay, so we'll make a note of that. So we go back to the beginning, and then we say, okay, from the first comparison, we can now conclude the index or the element, the indexes of elements that can contain this value goes from 256 to 510, because we just threw away the first half. Okay.
Would it be 257?
Sorry?
Would it be 257 because it's not 256?
No, it's not 255.
Oh.
Yeah, because the index that we use for the comparison is 255, so the next one, 256, can potentially be 3001 already.
That's the floor.
Yeah, so to do this calculation, I'm gonna cheat here because I can't do calculation that fast. So 256 plus 510, divided by 2 is 383, okay? So we go straight to 383, 383, which is this one here. That's a lot bigger. That's bigger than the value that I'm searching for, which means everything, including this element and after, I can throw away. So that means the range of indexes is now shrinking. The end of the range is now 382. Is that making any sense? Because I just compared to the entry at index 383, it is not what I want, okay? So the one before this one can potentially be a 3001. So the range of my indexes will go to 382. So we go back to here, and this time it is 256 to 382. And I do the calculation, which is the average of these two numbers. Just add these two numbers divided by 2. So the next entry I need to look is 319. So let's go to 319 and take a quick look. 319 has a value of 3687. It's still too big, so I have to shrink the end of the range to 318. Okay, so we have to shrink it to 318. Let me see if I can make the columns a little bit narrower because I'm running out of space. So 256 up to 318, and the calculation of the index is really just 256 plus 318. The whole thing divided by 2 is 287. So now we go to entry or index 287. 287 has a value of 3280. It's still too big, so I have to shrink the end of the range of indexes to 286. So 256 to what again? 86. There we go. And the average between these two, which is the index that I need to go to take a look, is 271. So we now go to 271. 271 has 3065, okay, which is too big. So now I have to shrink it again to 270, which is one fewer than 271. So the range is now 256 to 270. And the average is 256 plus 270, the whole thing divided by 2, which is 263. So now we go to entry or index 2, oops, too much. Oh, because this is a cool trick you can do with a spreadsheet. You can split the sheet into 2 halves using this tool. So now, when I scroll, they scroll together, but this side is always here. So I can go to index 263, which is this one here. It is too small. Okay, so now I have to arrange the beginning range. So the next range is going to be 264 to 270. And the midpoint of that is 267. So I go to index 267, 267. It is too big. So this time I shrink the end. So now it becomes 264 to 266. And the midpoint is, even I can do this calculation by hand. 265, right? So we go to 265, right there. It's too big. So we have to move the end back a little bit. Oh, but when we moved it back, where are we looking at? 264 and 264. This is the only entry left. I have just ruled out the entire array except for one element. Okay? So now this time we go to 264 and 264. I mean, the average is 264 itself, right? So that part is, this is an easy calculation there. We go to index 264, which is right here, and it is not the number that we're looking for, and therefore we can now conclude and say it's not there. 3001 is not in the array. Okay. But you can count the number of comparisons because each column, okay, let me see if I can kind of hide this part and extend this part here. This is the number of comparisons that we need in order to come to that conclusion. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9 comparisons. Does that make sense? 9 comparisons for 511 elements. That actually matches the other table that we worked on earlier. So are there any questions about what we just did? The process. Okay, that's binary search. Well, we just did it by hand. How do we write an algorithm to do it? That's the big question. Okay, because knowing how to do something by hand is good, but it's only the first step to write an algorithm. To teach the logic of something is one thing. To teach you guys how to write an algorithm is a whole different thing. Because writing an algorithm is quote unquote a creative process, but not in an art sense, but in a more of a problem solving sense. So I cannot really exactly tell you what went on in my mind as I try to derive the algorithm, but I can try my best to teach about the procedures, the mechanical steps that you can go through to figure this out. Okay? All right. So to do that part, I am going to rely on just a usual notepad here. And we'll start with revision 1 of the algorithm. In other words, the first thing we ask is, does this look like a repetitive process? We're doing something over and over again, even though each time something is changing, but it seems to be about the same thing. Is that, do you guys get that sense?
Yep.
Okay. So we know this is some kind of a loop, so I'll just say loop and loop, okay? And the question is, when do we get out of the loop? This part is going to be identical to what we talked about in the previous class. We get out of the loop when we either find the item that we're looking for, or we conclude that that item does not exist. Okay, so the description is not changing. Okay, when the item is found, or confirmed, or the absence of the item is confirmed. Okay, there we go. Okay, this is not algorithm at all. Yeah, there's no symbols here. Okay. Do you guys notice that in each iteration, for each step, we only do one comparison with a particular element in the array? Yeah, okay. So in order to designate which element we're comparing to, maybe using an index variable can be helpful. So the index variable, or the value of the index variable, controls the index of the item that we compare to. Okay, so we'll just add that here. So in revision 2, the only thing I'm going to do is to introduce m as an index variable controlling which element we compare in an iteration. There we go. Okay? I don't really know how to do the calculation. I just know there's an index m that we use to compare for each iteration. Okay? But with that, the item is found is now easier to express, because if the name of the array is A, then that means A bracket m close bracket is the same as k, which is the value that I'm searching for. It's the same thing as the item is found. Woohoo! I got that done. Okay. The other one is still a little bit kind of fuzzy. I don't know how to do this, so I'm just going to repeat this. The absence is confirmed. Okay. So now we can focus on, okay, we know the condition involves the array A, the constant k, which is the value that we are searching for, and the index variable m. We know that at least one of these has to change in order for a condition that is not true to eventually become true. Is that making any sense? Can we change the content of the array? Does that make sense? No, because we cannot change the problem itself. Can we change what we are looking for? No, because that's a given. Okay, you're supposed to find out whether this value is in the array or not by not changing the array or the value that we are searching for. That would be cheating, right? Okay, so we can't do that. What is only remaining is m. Can we change m? Yeah, we can change m, and in fact, if you go back to the spreadsheet, you can see how we are changing m for each iteration. Okay, good. So that means in the next revision of this code, in revision number 3, this is the best I can do to explain, how to come up with an algorithm in a step-by-step fashion. Okay, because there's a lot of stuff that I cannot really describe. It's a process in my mind that I cannot describe. Okay. All right. So the third iteration is basically saying, okay, but how do we come up with this m? How does it get updated for each iteration? Okay.
Average of the upper and the lower bound.
Okay, the average of the upper and the lower bound, because we saw that when we go through these calculations, right? Because each one of these, if you look at the equation, it is the average of the upper bound and the lower bound. Okay. So in revision 3, we introduce B as the lower bound, E as the upper bound, because one is begin, the other is end. Okay. If you choose L and U, that's okay too, but L looks like 1, and that's why I tend to avoid the use of L. Okay. So we are going to calculate M pretty easily. It is the floor of the average, so B plus E divided by 2, just like that, right? Okay. And then we do something here, okay, dot, dot, dot. Okay, we'll call it revision 3, because the most important point of revision 3 is we have to track a lower bound and an upper bound, and then M is the average between the upper bound and the lower bound. Okay, that's a significant step to the end, to the actual algorithm. That's fine. But I use dot, dot, dot to represent something here. It's like, well, if B and E do not change, M is not going to get changed either. Okay, so this code as it is doesn't make a whole lot of sense. The dot, dot, dot means, okay, we have to do something about B or E, but I'm not going to specify that code here. Okay, this is one revision. I'm going to take a little bit of time to think about it. Okay, so in the next revision, I'm more concerned about, okay, but how do we change the bounds? Excuse me. So when you look at these numbers, the bound of the next one is always kind of related to the index of the previous column. The index of the previous column is 255. This time we change the lower bound to 1 more than the index of the previous column. The index of this column is 383. The upper bound is 1 fewer than that. Okay, you can see how we kind of just kind of zigzag the way. Okay, so that means. Okay, so that means we know that sometimes we do one thing, sometimes we do the other thing, and the perfect control structure to do that is a conditional statement. Okay, so we're going to use a conditional statement here and say, I don't really know the condition, but I know sometimes we change the lower bound. So we change the lower bound to be m minus 1, and other times we change the upper bound. Oh, I take it back. This is m plus 1. We change the lower bound to the previous index plus 1, and other times we change the upper bound to m minus 1. Okay, but I am going to leave this as dot 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 because I need to do my dishes. In other words, I am not taking on the algorithm and try to finish it in one single shot. Okay, I work out one piece at a time. I leave certain things, they're like, okay, I'll figure this out later. But I can identify certain things. Okay, this is a puzzle. Okay, you don't put together a jigsaw puzzle linearly. Okay, you don't just go, oh, I'm gonna do a printer thing and I'm gonna solve this puzzle in a linear fashion. You look at all the key pieces, right? When you work on a real jigsaw puzzle, what do? What are the pieces that you start with?
Edges.
Corners, and then edges. Okay, you don't start right in the middle. You don't just go. You don't go like a printer going, scanning in scanning mode. It doesn't make a lot of sense. So it's the same thing with algorithm design. You start with the corner pieces, the pieces that will anchor the other pieces. Okay, which is what I'm trying to do here. Okay. All right. So let's go ahead. This is revision 4. Okay, in revision 5, we try to be more specific about the condition. So let's copy and paste this here. Okay. But the most important part is you have to finish this, with a manual example first, because otherwise there's nothing to refer back to get your inspiration of, okay, but what is the condition that determines which way to go? With my case, because we do have an example here, then we can go back to this and go like, oh, so the ordering between the number that we're trying to find, which is 3001, and the value of the element at that index, which one is greater determines whether I should update the lower bound or the upper bound. Okay? So now I can go back to my algorithm and say, oh, okay, I kind of know what this is about. It has to do with at least the comparison of k to the element at index m, okay? So the only question is, when do I need to update the lower bound to change the lower bound, and when do I need to change the upper bound? That's the only question. To change the lower bound means I'm ruling out more stuff that is less than the value that I'm dealing with. So that means k needs to be greater than a bracket m to move my lower bound. Is that making any sense? Now you can always go back to the example by hand to verify this is the right ordering, because you just apply this logic here and say, oh, when the value that I'm searching for, 3001, is greater than the value of the element at index m, is that the time when I update the lower bound? You go back to the example, yes, it is. Okay, so that's a confirmation. That's why it is important to do it by hand first and have a log of how you do it by hand. Okay, the other one, I cannot be just an else because the else can also be equal to. So this is the trick of using else if, and you say, okay, the other case is when k is less than a bracket m, then we want to update the upper bound. What if they're the same? Well, if they're the same, we're done. There's nothing to do. You don't have to update the lower bound or the upper bound because we're done. Okay, so that's revision 5. We still have one unsolved puzzle, which is how do we know the absence is confirmed, the absence of the value that we are searching for. So that's for the next. When they overlap, when they cross over, I should say. Okay, so we'll take all this stuff here into revision 6. So in revision 6, I focus on the one piece that is not specified, which is how do we know the number is not there? So if you remember, from your perspective, the lower bound starts all the way at the beginning, the upper bound starts all the way to the end. So we are moving stuff kind of like this. They get closer and closer. At one point, they can be the same. When they are exactly the same, we are not done yet, because we're basically saying there's one element left to take a look at, okay? But if that element does not match, and we apply that logic, we are either moving the end this way, or we're moving the beginning this way, but they cross over. That's the indication that we don't have anything left. So we say when the beginning is greater than the end, then we are done. Because that's the conclusion. The element cannot be in the array when the beginning is exceeding the end. But that also jives with the initialization of the first element, or the index of the first element before the first comparison that can have the value that we are searching for. It's really just the first element of the entire array. And the last one is the index of the last element of the entire array, because before the first comparison, I have no idea, where the value can possibly be. So I have to say, well, it can be anywhere in the entire array, which means the range of indexes that I have to consider is going to be everybody. Is that making any sense? And in this particular case, it doesn't make sense for this to be a pre-checking loop. Why not? Just look at this code here. Why do you think this has to be a post-checking loop?
Do at least one comparison.
You need, well, it's not just the comparison, it's M itself. M doesn't get a value until we get into the loop. So if this is a pre-checking loop, then M will be uninitialized when we perform the comparison. So that means it is a post-checking loop using repeat until, and we are right on time. I can get to my building design committee meeting on time.
What's the acronym for that?
I have no idea. They are still going to name the building too. I don't know how they want to name the building. I'm just very tempted to call it STEM Unit 1. SU1. It's as opposed to SG1,
That was a great show.
Great show, exactly. Alrighty, so I hope you guys have a nice break. Don't come back next Monday because nobody's going to be here. So have a nice spring break. Don't forget your homework assignment though.
It's like a deep purple.
Sorry.